How did the universe come to be? Why does it look the way it does? How did galaxies form? Planets and solar systems. Life. To find the answers, a series of missions has transported a battery of high-tech instruments above Earth's atmosphere. To peer into the most violent processes in nature and explore the mysterious workings of the high-energy universe. Decades ago, high-energy astronomy was motivated by a number of basic questions. Do supermassive black holes really exist? What are quasi-stellar objects, or quasars? Are they solitary objects in the vast darkness, or are they part of larger structures? In the early 80s, a diffuse X-ray glow was seen filling the night sky. What was it? Bursts of ultra-high-energy gamma radiation appeared almost once a day, lasting seconds, or as long as a day. Are these events nearby, even within our solar system? Or are they extremely distant and highly energetic? Finally, astronomers suspected that supernovae were violent explosions. But what was their exact nature? We now know that they are the final moments in the lives of large stars, and that they are the source of elements that make up our bodies: calcium, iron, carbon, and so on. Because high-energy light does not penetrate our atmosphere, scientists launched a fleet of space observatories designed to capture wavelength bands from gamma ray to infrared. These wavelengths tell us the temperature of matter in an object. Gamma rays and X-rays, tens to hundreds of millions of degrees. Ultraviolet, hundreds of thousands. Visible light, tens of thousands. Infrared, hundreds of degrees. Here is a Hubble Space Telescope image of Cassiopeia A. It shows the visible remnant of a supernova, glowing at about 10 or 20,000 degrees Celsius. Here is an image from the Chandra X-ray Observatory, showing gas heated to tens of millions of degrees. Some of the first images from the Hubble telescope in 1994 captured the galaxy M87. For the first time, astronomers spotted the hot gas swirling around its central region. Knowing the scale of this picture and the speed of the gas, astronomers discovered that within a volume of less than a solar system, there is an object that weighs some 3 billion times the mass of the Sun. Nothing that dense can be anything but a black hole. Over the following years, additional discoveries showed not only that supermassive black holes exist, but they lurk at the core of every large galaxy, including our own Milky Way. This animation shows a black hole moving through space. As an unsuspecting star gets too close, the black hole's gravity tears it apart. That creates a so-called accretion disk of hot gas and dust rotating rapidly around the black hole. Within the disk, charged particles spin off magnetic fields. They channel some of the inflowing matter out in jets so powerful they move at nearly the speed of light. The closer you get to a black hole, the higher the temperatures, 10 million or more degrees. As a result, if you want to study the inner parts of the accretion disk, you have to look at high-energy gamma and X-rays. This inner region can be hot and bright enough to shine across the depths of space, becoming a quasar. The brightest and most active quasars are probably consuming matter at a high rate. In this Hubble image, we see a radio jet coming out of the center of a galaxy. Zooming in, we see the accretion disk and a dark central region. Like Sauron in his dark tower, black holes are known for being terrifying, invisible sources of death and destruction. Black holes are such powerful gravitational monsters that they warp and twist the fabric of space-time. If you get up close, you'd see something like this. An accretion disk visible from both above and below. There is an inner ring caused by light that goes all the way around the black hole before escaping and eventually making it to us. It's actually difficult to get close to a black hole. Gas orbiting the event horizon can never actually reach it unless it first sheds its angular momentum. To understand how this can happen, watch a roller skating maneuver in which one skater catapults the other forward. The skater on the inside whips the partner around, transferring angular momentum outwards and slowing down in the process. Around real black holes, it's magnetic fields that sap the angular momentum of the disk, allowing some gas to fall in while throwing the rest out into space. Like rubber bands, these magnetic fields can stretch until the point where they snap, releasing massive amounts of energy and heating the gas to millions or even billions of degrees. You can see this in the magnetically active corona of our Sun, where superheated gas shines very brightly in X-rays. One of the remarkable effects of a black hole's extreme gravity is predicted by Einstein's theory of relativity. It holds that space-time is not only curved, but twisted. In this computer simulation of particles plunging into a black hole, you can see the effect of this twisting right outside of the event horizon, where particles are being swept around in a counterclockwise swirl at nearly the speed of light. Taken together, the pulling, twisting, and slinging of gas by the black hole leads to ultra-high energy particles and powerful jets. We're just beginning to scratch the surface of what Einstein's theory predicts. Today, the New Star mission is the first telescope to look at the universe in high energy or blue X-rays. This is a Hubble Space Telescope image of the nearby galaxy Messier 82, seen in black and white. This is what its warm, dusty regions would look like if you could only see it in the red, orange, and yellow of visible wavelengths. New Star was able to make high-energy X-ray images of the region around the supermassive black hole in the heart of our Milky Way galaxy. When the universe began, it was a soup of hot hydrogen and helium gas. $13.8 billion years later, we are surrounded by a rich mix of chemical elements, ranging from the nitrogen in the atmosphere to the calcium in your bones. This movie follows the evolution of the universe as portrayed by theorists using supercomputers. Filaments of hydrogen and helium form, shaped by the gravity of dark matter. In these filaments, clouds of dust and gas condense and form stars. The massive ones burn hydrogen and helium, creating progressively heavier elements like carbon, nitrogen, oxygen, and eventually iron. When these stars run out of nuclear fuel, they can explode in dramatic supernovae. As the universe grew older, countless generations of supernovae spewed chemical elements into the cosmos, where they condensed into galaxies, stars, and planets. How we know all this is, in practice, a dance between theorists and observers with telescopes, including infrared, optical, X-ray, and gamma-ray missions. Huge computational power and theoretical resources have gone into understanding the life cycles of stars. Here is a recent attempt to simulate a stellar explosion in a supercomputer. You can see here that the explosion halts. The authors of the experiment then inserted a theoretical sloshing of gas in the central part of the star, setting the supernova in motion. To find out whether this happens in nature, astronomers enlisted X-ray telescopes to take pictures of the remnants of supernova explosions. Here are images of the debris from the historical supernova remnant Cassiopeia A. The red and the green images were taken by the Chandra X-ray Observatory, which sees the universe in red and yellow and green colors. NuStar has added the blue. This combination gives us a window into the heart of the explosion. These observations suggest that the shape of the explosion was bubbly, consistent with the sloshing mechanism predicted by theorists. Here's Cassiopeia A in all its panchromatic X-ray glory. High-energy telescopes in space are revealing violent events in whole new ways. That includes the most violent of all, a gamma-ray burst with the energy equivalent of 1 to the power of 30 H-bombs. That's 1 with 30 zeros after it. They're the most energetic explosions in the universe. They occur about once per Earth day, and in every part of the sky. In the early days, they were the subject of intense speculation. Aliens in outer space, alien wars. This was an actual newspaper article. In 1998, an Italian and Dutch satellite discovered that gamma-ray bursts actually originate far outside our own galaxy. That means they must be extremely bright, energetic events. A pair of satellites, called Swift and Fermi, were launched to study them in detail and to push the frontiers of high-energy astrophysics. To date, they have detected over 1,000 bursts. Every time the Swift or Fermi satellites detect a gamma-ray burst, scientists get a page that sends them running to their computers to view the data. What they have learned is that gamma-ray bursts are generated by supernovae so powerful their cores collapse to a black hole. A small fraction of the matter flowing into the black hole escapes in jets. When the jet is aimed at us, we see it as a gamma-ray burst. Gamma-ray bursts are so intense that they can destroy the atmospheres of nearby planets. we appear to be safe, at least for the time being. Imagine a dark and clear night. Overhead, the Milky Way spreads out across the starry sky. The beauty and grandeur of this portion of our own galaxy beckons us to ask our deepest questions. What is the nature of this marvelous universe? How large is it? How did it come to be? And are we alone in this vast cosmos? Astrophysics, the study of the universe and how it works, is central to our quest for answers. We are beginning to find them, thanks to instruments sent up into space, beyond the limiting effects of our atmosphere. High-energy missions, Fermi, Swift, New Star, and Chandra, are uncovering a dynamic universe that is dramatically different from the tranquil tapestry we see with our eyes. They show that the cold, dark reaches of space are punctuated by turbulent forces. Black holes, cosmic explosions, bursts of radiation, that violent energy is very much a part of the universe. As we ask once again the great questions, we know that what we see is just the beginning of a story, written in the great rumblings of the cosmos. A story that is unfolding still. To find the answers, a series of missions has transported a battery of high-tech instruments above Earth's atmosphere. To peer into the most violent processes in nature and explore the mysterious workings of the high-energy universe. Was it? Bursts of ultra-high-energy gamma radiation appeared almost once a day, lasting seconds, or as long as a day. Are these events nearby, even within our solar system? Or are they extremely distant and highly energetic? How did the universe come to be? Why does it look the way it does? How did galaxies form? Planets and solar systems? Life. What are quasi-stellar objects, or quasars? Are they solitary objects in the vast darkness, or are they part of larger structures? In the early 80s, a diffuse X-ray glow was seen filling the night sky. What? Decades ago, high-energy astronomy was motivated by a number of basic questions. Do supermassive black holes really exist?